Hello everyone, today let's solve Leetcode problem 437 path sum 3. So given the root of a binary tree and an integer target sum, we need to return the number of paths where the sum of all the values along the path equals a target sum. The path doesn't need to start or end at the root or a leaf, but it must go downwards, right? So here are two examples. Example one is, so we can see this tree and target sum is 8. So we have 5, 3, 5, 2, 1, minus 3, and 11. There's three paths, right? And this is example two. But I think example one is straightforward enough. So here are some things we need to keep in mind. First of all, every path we're just finding like eligible paths, right? Eligible paths um that can sum up to target sum, right? And one thing to keep in mind is that even one node could be a path. So if for example, if our target sum is 5, then this 5 is also eligible, right? This 5 is eligible. And another thing is that it's a binary tree. It's not a binary search tree, so it doesn't have any like rules or any qualities like left subtree must be smaller. Like everything in the left must be smaller than everything on the right. So this rule doesn't is not found if it's not really like isn't valid, isn't applicable for this binary tree. It's for BST, right? So as a result, in order to find eligible paths, we have to traverse through the tree. Yeah, there is no branch we can ignore. So that indicates the use of either pre-order traversal or in-order traversal or post-order traversal or whatever. And another thing is that um, even if we encounter -3, that cannot discourage us from exploring further because it's a binary tree. It doesn't have any, it doesn't have any BST quality, right? So for example, like yeah, so let's say um, we don't have very good examples here, but so let's say, oh, if our target sum um, is 11, right? Then once we encounter this -3, we can't be discouraged. We can't say, there's no way we can find that 11 in this path. Or let's say if our target sum is, um, if, let's say if it is, um, so another example could be if target sum um, is 5, and instead of -3, we have a 6 over here. So one case is that we encounter 6 and 6 is greater than our target sum, so we don't explore further. But that's not the case because the next node might be -1, right? Because everything in this binary tree is pretty much arranged randomly. So we have to explore the whole tree in order to find eligible paths. So that's some advice. That's some very important points we need to be mindful about. So as I said, the overall strategy is that we have to traverse the whole tree. And for this problem, I'll just do in-order traversal. And when we do pre-order traversal, and when we do pre-order traversal, so let's try the pre-order. Okay, so the first case is that if root is null, then we just return 0, right? Um, because yeah, because if we just take a look at the constraint, number of nodes could be 0. So if it's 0, then we just return 0, right? Else we do pre-order, and we need a passing root as well as target sum, right? And so we can keep a global variable called count, and basically we will modify this count in the pre-order traversal, and the only thing left in path sum function is just to return count. Then let's fill out pre-order. So the very important tip for pre-order is that we need a, so first of all, if root is null, right, we just return. That's our base case. Then we need to process the root first. And what's the processing? What's the what should we do to process the root? Well, we can't just call pre-order on the root, right? Instead, we need to have a helper function to process the root, and the helper function basically specifies what we want for this problem, which is what we want to find eligible paths, right? So what we can do is first of all we have we can have a helper. We can call it a helper, or a better name is find path, right? So we can call find path on root, and we can have a sum 0. Basically, when sum is equal to target, we can increment count. So that's the thing. Yeah, and another thing to keep in mind is that so finding a 5. So for example, if our target sum is 5 and we encounter this 5, finding a 5 is not sufficient. It's not enough for us to not to explore further, because we can have something like 5, 3, minus 3, or 5, 1, minus 1, and it is also eligible. So even if we find a value, even if our current sum is equal to target sum, we still cannot stop. We have to explore further. So that's the idea here. Something we need to keep in mind. So the initial sum is 0, and we also need a passing target. And because it's pre-ordered, then we can just call pre-order on, first of all, the left subtree, and we need a pass target, and then the right subtree, and we pass in target, and that's it. So now let's fill out find. Okay, so we have tree node, which is root, and we have current sum and target, right? So first of all, if root is null, then we just return, right? Else. So so first of all, our current sum start at 0, and whenever we encounter a node, our sum will increment the value of the node, right? We'll just our new sum will be 0 plus root value, right? And so we need to update our current sum to be current sum plus root value, right? Because we have to explore that node. We have to start from that node. If we don't even increment with the value of that root, then it doesn't make any sense. Then it's like we just don't explore that node, right? So we have to increment by the value of the root first, and then we need to check if current sum is equal to target. And then what we do is to increment our count. But as I said, this is not enough. This condition is not enough to let us stop, to let us return, because we can have something like, so if our target value is 5, then we can have a branch like 5, 1, minus 1, or 5, minus 1, 1, and that also sum up to 5, and that is also an eligible. It's a good path. It's a path that we should consider. So we only increment count, and we still need to go on and explore. So if current sum is not equal to target, either it's greater than target, or it's smaller than target, or it's equal to target, we need to move on to explore, right? So the next step we need to do is to continue. First, we start at the left, and current sum and target, right? And then we find right. We find the right subtree, current sum, and target. So that's it for this function. So that's it for this whole solution. And let me just run the code, see if we can pass all the test cases. Okay. Find path. What is this? undeclared. Oh, I see. Oops. Here is another one. Okay. Other two. All right. So as you can see, it's accepted and okay. All right. Oh my God. So let's just change it to long long. All right. So as you can see, our runtime is efficient and memory is efficient. So basically, the overall strategy is that we need to use pre-order traversal to loop through the whole tree. And in pre-order traversal, we have to process the root first, and then we move on to the left subtree and right subtree. And the way we process the root is to find if there is any eligible tree or any like any tree that could sum up to target sum, right? So that means we need to have a specific helper function to process the root. And our helper function in this case is find path. So that is the overall strategy. Hope you enjoyed this video and thank you very much for watching it. Have a good day.